I guess I just changed the settings of the microphone because it was over amplified. And let's see. Okay, is it not too loud? Okay. If you hear weird noises in the background, like kind of paper crushing noises, it's my naughty cat. Who is has to be hungry in the morning today because he is going to the vet, and he's very angry and he's doing it. So unfortunately, you might hear it. Okay. Maybe we could wait still a little bit, or let's start with the questions. Are there any questions to last week's lecture? I just realized that I didn't upload the part on checking whether a string can be generated by a grammar using the CKY parsing method. Do you want me to add that, or was that clear how it's done? And you don't need this small set of slides. Okay. Yeah, then I'll format it because it was in a somewhat different format. Then I'll format it and add it to the previous section on CKY. Okay. If there are no questions, we could start already. Last time we finished at basically we were done with CKY parsing, and today we'll move on to dependency. And CKY parsing was an example of parsing of constituency structures, so phrase structures. And today we'll move on to dependency grammars. I already introduced the notion of a dependency grammar earlier. Dependency grammar models the relations between words in a sentence directly. These relations are called dependencies, and the dependency tree represents those relations explicitly in the form of a tree in which the nodes are the words and the edges are relations. And in case of a labeled dependency tree, these relations get explicit names. So here you have an example of such a graph representation of a sentence that builds on parts on immigration were submitted by Senator Brownback, Republican of Kansas. So as you see, each node represents a word. The higher node is usually referred to as the head. So here in this relation, the head is submitted, and the dependent, the node that the subordinate node is usually called dependent, or a modifier. The head is can be also referred to as governor because it governs, in a sense, what is subordinate with respect to it. Some types of relations lend themselves better to being called modifiers. For instance, we can talk about adjectival modification, so the equivalent of a syntactic equivalent or dependency tree equivalent of an adjective in a dependency structure would be an adjectival modifier. And in this case, this modifier is more intuitive to understand. In general, all these dependents are, all these subordinate nodes are called dependents. And yeah, you have the relations labeled on the edges. And usually these dependencies form a tree in case of well-formed sentences, of course. And this is a connected acyclic tree, and it has a single head. Of course, sentences that are not well-formed might cause problems for dependency analysis, and then these trees somehow are forced into ill-formed structures, sometimes to create something that is as close as possible to what would be a valid dependency tree. What types of dependency relations are there? So you see here some examples of dependency relations. Some already look familiar from part of speech tagging. They even, in some cases, have the same, in cases of some of parts of speech tag sets, have the same acronym or label. However, in many cases, syntactic dependency relations have their own names. Here is an example of what is usually referred to as universal dependency relations. Universal because they are thought to hold between words in a sentence across most languages, or some languages might have other dependency relations depending on what language phenomena the given language exhibits, but many are common. Here are examples of clausal argument relations. So, and these are, of course, acronyms or labels, specific symbols specific to this specific instantiation of dependency relations, universal dependency relations. So with n-subj will label nominal subjects. With d-obj, we will label direct object. So an object between which nothing intervenes between this object and the verb. So the object directly follows the verb. I-obj would be an indirect object. So this would be an object which is separated from the verb with another object, for instance. So in a sentence, Mary gave Peter flowers. Give is the main verb. Mary gave Peter flower would be the direct object, and flowers in Mary gave Peter flowers. You see there's Peter intervening between that object and the verb. So flowers would be referred to as an indirect object. Clausal complement, something that is introduced in English by that or which. And an XComp, this is a little more complicated. An open clausal complement. You don't have to go into details of all those relations, and some of the more complex ones we will not require that you know details of. But the basics, such as subject, direct object, indirect object, of course, you should know. Similar here, these are modifier type relations, nominal modifiers, with the most basic case, n mod, nominal modifier, so it's a modification by a noun. A mod, modification by an adjective. Num mod, modification by a numeral type part of speech. Apos is an appositional modifier, so an interjection. For instance, here you had such an apposition, Senator Brownback, Republican of Kansas. It elaborates this nominal phrase here, and here is the appositive relation. That is a determiner, so a simple determiner. Case are all sorts of prepositions, be it in postposition or other case markers. This is a rather broad category for any type of prepositional modification. And there are other relations. Conj is a conjunct. This is a relation that you should remember. Coordinating conjunction is a conjunction with an and or an or, so a coordinating structure. Of course, these set of dependency relations may differ depending on a grammar formalism or somehow a model of dependency that is adopted. Here what you see is just an example. Here are examples of the different relations within sentences, some of the relations within sentences. So here's an example of a subject dependency. United canceled the flight. United is the subject of the sentence. Had is the head of the sentence, and United is the dependent in the function of a nominal subject. United diverted the flight to Reno. Direct object, diverted is the main verb, the flight is the direct object. Or we booked her the first flight to Miami. there is a mistake here. These two sentences should be swapped. We booked her the first flight. The flight to Miami is a direct object, and we booked her the first flight to Miami is an indirect object. So, sorry, this will have to be swapped. These two, I will make a note of that and redraw this table. Nominal modifier, we took the morning flight, so the head is the flight here, and morning modifies that flight, and morning is of course in here in the function of a noun. Adjectival modifier, book the cheapest flight. Flight is a head, and the dependent in the function of an adjective is here cheapest. Numerical modifier, before the storm, JetBlue canceled 1,000 flights. So you have the head flights here. 1,000 is a number, so you have a dependency modification by a numerical token. A positive, united, a unit of UAL, match the first. So here is an example of this kind of interjection by a small unit, in this case a nominal phrase. In a function of dependency, this kind of dependency function is called an apposition or an appositive modification. Determiner, this is easy. The flight was cancelled. Which flight was delayed? Any kind of determiner falls into this category. The head would be the noun, and the determiner is the modifier. Conjunction, you see here, two coordinated sentences. We flew to Denver and drove to Steamboat. Fly is the head verb of the first coordinated clause, and drive in the past tense is the head verb of the second clause, coordinated clause. And these two verbs with respect to one another are in the conjunction relation. The conjunction itself here, and this is the same sentence, is in this conjunction relation, coordination relation with respect to one of the verbs. In this case, it's the second verb. It's also a kind of an agreement which verb the conjunction itself, coordinating conjunction itself attaches to. And here's an example of a case relation. Book the flight through Houston. Houston will be the head, and through preposition will be an example of a case relation. Is this clear? Are all these grammatical relations clear to you? Is this new? This set is basically what is a good set to remember. You don't have to remember all of the dependency, universal dependency relations, but there might be a question in exam that asks about dependency relations, and you should be familiar with some of them. You will, like I said, you don't have to memorize them. You'll get a list if there is a question with the relations, but you should be able to interpret these relations, what they are, and above all, being able to assign relations to sentences, such as here. Is this, are these relations clear? Is this familiar, or is this all new? Basically, I don't know what your background in linguistics is. Not clear, but all new. Okay, so like I said, you don't have to memorize it. You have to understand. Here are examples of the relations with explanations, with descriptions, but you don't have to memorize these symbols, of course. So it makes no sense. You should be able to recognize them once you see one. When you see one, okay. How to identify dependency relations, and how to identify or somehow recognize a dependency structure in a sentence. Well, this is a complex problem. Basically, this is a problem of parsing dependency relations, or parsing into dependency trees. You already know that the ambiguity phenomena in the language, these ambiguities may lead to alternative parses. Some of those parses will be valid alternative parses. Some will be somehow represent spurious ambiguity. But there are certain um, signals that um, serve as guides to identifying the probably intended parts of a sentence. So some dependencies are basically more plausible than others. Some are obvious. For instance, determiner relations are quite obvious. Distance often is a good indicator. Dependencies tend to hold between nearby words, so the distance should be as close as possible for English. There are languages, though, with so-called long-distance dependencies. An example of such language is German and general Germanic languages. German has those long-distance dependencies. An example of that would be particle verbs, in which particles in German may be represented with dependency relations, and sometimes these particles end up at the end of a sentence with specific constructions. Even more complex relations exist in Dutch. But we don't have to go into details. But in general, distance is a good indicator. Breaks are also a good indicator. You can look at verbs or punctuation. Dependencies rarely span across clauses or there's intervening verbs. You can also look at phrasal or intonational prosodic structure of a sentence, and this is a good indicator of where to place dependencies or relations. Valencies, so the predicate argument structure of a given word, is a good indicator. Usual number of dependents for a head will be represented probably on each side of that head. So if there's a verb with two arguments, you can expect that there will be two dependency relations of some type on both sides of the verb. So here is an example of a sentence. Discussion of the outstanding issues was completed, and you see that there are most of the relations are local. However, there are many options how you could draw the dependencies. And there are also conventions as to how the trees are actually drawn. So here you have an example with a determiner being linked to the noun, and the adjective being linked to the noun. Here's the head verb. So from the head verb, you have a link to the noun, which is the subject of that sentence, and that subject has dependents indicated by this preposition here. This tree in general is an unlabeled tree. So the basic task is in dependency parsing is to identify the structure itself. And the task of labeling the tree is a task of its own. But the general task is basically to decide how to build these links, how to build the relations between which tokens, between which words in a sentence. Okay. Here is another example. Retail sales drop in April cools afternoon market trading. Here you have basically different possibilities for interpretation, because this sentence is a kind of an ambiguous sentence, in a sense that when you read it fast for the first time, you have to think about what the main verb is. The first candidate for the verb is this word drop here, but in fact the main verb is cools, and so the parse has to be, even with human parse, we make a double take here and reparse the sentence probably for most humans. Okay. So once again, to summarize the difference between phrase structure grammar and dependency grammar, in phrase structure grammar, the tree is consists of nodes labeled with phrase labels, and the trees form phrasal structures. Whereas in dependencies, the trees are formed from nodes which correspond to words, and the edges correspond to dependency relations. Whereas here you have the edges. You could, in principle, say which verb phrase it is on the edge, but the words are at the leaves. So it's an entirely different approach to representing the structure of a sentence. Okay. Now, we already saw how to parse phrase structures such as this one using one specific algorithm. And now the question is how to parse this kind of structures and how to build these dependency trees, and especially labeled dependency trees. So trees which not only have edges here between words, but also labels which denote dependency relations. In general, there are two approaches to parsing. We already saw one approach. The CKY algorithm is an example of a bottom-up parsing. In this approach, we start evaluating the inputs from the leaves and move up and build a tree. So basically, oh, sorry about this spelling mistake here. We reduce the input string to the start symbol in the grammar. It can be viewed as reducing the sentence itself to the start symbol. So by putting together the leaves, we want to put together a structure that in the end forms the start symbol. In the case of natural language sentences, this will be the sentence symbol. So we search for production rules in general, which reduces a string to that start symbol. We already saw one example, CKY, for phrase structure parsing, and today we'll talk about shift-reduce parsing for dependency trees. There's also a different approach to parsing. We didn't have examples of this approach. This is an early approach to parsing. Top-down parsing, we start evaluating from the root and move down, basically. And we try to find in a way, a leftmost derivation for a string. So we collect productions from by expanding the so-called right periphery. So we are basically searching for a production rule that can be used to construct that string. So here we are constructing the strings, and here we are decomposing the strings into the start symbol. An example of this kind of top-down parser is one of the early algorithms introduced by early. There's also more recent approaches to top-down parsing, but we will not go into details. Again, here we will talk about an approach to building dependency trees by means of so-called shift-reduce parsing. This is an example, this is here. This is an example of so-called transition-based parsing. And we will be basically in this approach will be in general making operations, will be consuming symbols from a sentence and using operations to either remember the currently consumed symbol or push that symbol, or rather shift that symbol, and obtain another symbol and make choices about how to attach the newly consumed symbol. So it's basically a set of transitions in a pass through a sentence. Yeah, so this is the core idea of shift-reduced parsing. In general, it's an example of a bottom-up parser. We read the input from left to right, and we, of course, have our grammar. and try to match a right-hand side of some production until we get to a start symbol. So we will be attaching these productions. Will be basically collecting productions, reducing this tree. Each left-hand side will, for each right-hand side, will substitute on the left what's on the left-hand side, so that in the end we'll end up with the start symbol, which is the final symbol on the left of some left-hand side of some rule. There are some basic concepts in this parsing, in this approach to parsing, typically referred to as configuration. We will have a stack on which we'll remember the symbols consumed. We'll have some input buffer of words or tokens, and we'll have a set of relations that will represent a tree, in our case, dependency trees. And like I said already, parsing is viewed as a sequence of transitions through the possible of configurations of these three elements, with the goal of finding the final configuration where we've consumed all the words and the dependency tree has been generated or synthesized. At the beginning, the initial configuration is that the stack contains the root node of the sentence, and the word list is initialized to basically the words or tokens, lemmatized tokens from the sentence, and we have an empty set of relations. And the goal state that we want to arrive at is the stack and the word list being empty, so we've consumed all the words. We've transitioned through all the words, and the set of relations represents the final parse. We'll use typically a breadth first search, and we need some kind of stopping condition. Basically, we stop when the start symbol has been popped from the stack. So we have arrived at the sentence that can be generated by our grammar. Okay, so here we have our basic setup. We'll have a stack, a data structure. We'll have a parser. This parser will be making decisions about how to attach relations. We'll have our input buffer here, and we have our dependency relations here. And this parser will be making decisions about what to do with these dependency relations. And this approach that we'll talk about here, typically look at first two elements in the stack, and we select an action from a set of actions. There will be two types of actions based on a decision from an oracle, so something that we assume knows what the right decision is, and this oracle will examine the current configuration, make a decision which relation to pick at a given point given the current configuration. Okay, so what are the actions that we'll be taking? We'll be assigning the current word as the head of some previously seen word. We are building dependency relations, so we'll be basically building these substructures of head dependence. So we can assign a word as the head. We can decide to assign some previously seen word as the head of the current word. So basically, the current word will be a dependent. Or we can postpone doing anything with the current word and add it to a store for later processing. So basically, we put it on that stack list. Specifically, there are two main operations, two types of operations, you could say, because with this specific approach, there will be more operations, more specialized operations, let's say. We will be shifting, so pushing the current symbol into the input, in the input onto the stack, and we will be reducing. These are, of course, kind of this is terminology from stack, but this reduce is kind of terminology, an abstract terminology related to what actually happens with the tree. So we're reducing if the some n words on the stack, we'll be using 2 words, match some right-hand side of the rule, then we will pop those words and replace them with the left-hand side of the respective production. So if you find something that matches something on the stack that matches some right-hand side of a rule, then we will replace it with that left-hand side and pop it from the stack. So in that sense, it's reducing because the left-hand side will be in a sense of smaller complexity than the right-hand side. Okay, in the specific implementation that you will also use for your lab exercise, we'll use a specific approach to that is typically used in dependency parsing, which specifies or makes the reduce operation specialized in into 2 specific relations. Oh my God, operations. Sorry, the left and right reduce. So the left arc operation will assign a head-dependent relation between the word at the top of the stack and the word directly beneath it. So remove the lower word from the stack, and the right arc will assert or assign head-dependent relation between the second word on the stack and the word at the top. So it will also remove the word on top of the stack. In the first case, it's the lower word, and in the second case, it's the top word, and it will basically correspond to the left and right branch of the current head. Shift will remove the word from the front of the input buffer and push it onto the stack. So we have our input coming in, and Shift will consume the first token and push it on the stack. Could you reread this and make sure that this is clear? The arc is that not for a purpose. The arc represents the left and right arc in the tree. In the resulting tree, right? Yes, it's one of those. Yeah. So this is okay. Yeah, so there are different approaches, and it's also somewhat different terminology, somewhat different definitions, but the general idea is always the same. So there may be a different set of reduce actions, and this depends on just an approach, and you have to grasp basically the general concept. The most basic shift reduce, actually the most basic concept is here. There is a shift operation and reduce operation, and how this reduce is specifically realized, it differs between approaches. But shift typically will push a word. This is typically always the same. Okay, let's go to an example. There is still a bit of an interruption. So we always operate on the words on top of the stack, or on the first 2 words on the stack. And once a word has been assigned its head and removed from a stack, it's not available for further processing. So it's only a single pass. Single pass through a sentence, and this has there are also certain preconditions. These are details. These are details that you can read later. The basic algorithm is rather straightforward. we start with an initial configuration, and until the state is not final, so until we've reached the start state S, we ask a coracle for a decision. So we choose a transition operation to apply, and apply it and create a new state. And we loop through this until we've reached the start state S. So we can't, and basically the buffer of words is empty. Yeah, so parsing is a single pass left to right through the tokens. Every word must be shifted onto a stack and later reduced. And the process ends when all the words have been consumed and the root node is the only element that's on the stack. What is the oracle, and how to hire an oracle, where to hire it? Well, an oracle is that decision system that is consulted for a transition to use in a current configuration. And it produces, as a result of applying the transition, a new configuration is produced. This is typically done by a greedy algorithm with a single choice. No other options are explored, so there is no backtracking. It's a single parse that is returned. And this oracle we'll get to briefly in a moment. Just see that someone, Mati is typing. Yeah, exactly. Just like I said, there are different approaches. You can either have access to only the top element, depending on the approach, only the top element on the stack, or the top n elements on the stack you saw here. That it could be reduced n. So the top n words on the stack might be available for reduce. Yeah, that's the difference. Okay, here's an example of what this kind of stepwise transition through a sentence might look like. In the beginning, we start with a full sentence. And let's say after the step one, where we've shifted the book, on the stack we have book and the root. On the word list we have me, the morning, and flight. We push me on the stack at this point, and we consult an oracle that knows somehow that the right operator to use here is the right arc, and we assign the book as the head of me and pop me from the stack. So in the step two, we have in the step two, after step two, we've popped this me, and me is no longer available for processing. And the word list is this. So this is an example between 2 and 3 where a word is popped from a stack. And automatically we know that the right action is right arc. And if you analyze further, this I will leave for you to analyze at home. The right transitions are marked here. The right operations are marked here. Okay. So, what are the problems with this approach? Of course, the first problem is that there is only a single pass. So once we've made a decision about the transitions, about the actions, that's it. And we can't trace back in the basic approach to either build an alternative parse or correct the parse. And of course, a specific sequence may be ambiguous and might lead to more than one reasonable parse, because we have this problem of ambiguity. So other transitions may lead to equally valid different parses. this specific approach will return on 1. The assumption is, of course, that the oracle is always provides the correct operator. This is, of course, not likely in practice. Some incorrect choices will be made and will lead to incorrect parses, because we're dealing with single pass parsing here. In order to produce labeled trees, so in order to give labels to those arcs, the set of reduced operation is expanded and parameterized with respect to dependency relations. So what you will see is something like left arc and subt, where this end subt represents the label on the relation that is introduced, so on the arc that is currently introduced, or the opt for direct objects, and so on. So the set of transition operator is expanded basically to include all the operators for left and right for each relation in the dependency, in the set of dependency relations. Now, where to get the oracle? The oracle you might hire from machine learning, and specifically, you've already heard about dependency tree banks. You might apply a tree bank and parse that tree bank using an oracle-based approach. So learn the labels for each of the for each of the arcs based on the tree bank, and so train this oracle. And once you have trained this oracle, you can use the oracle to make decisions. So with using machine learning, an oracle can be trained, of course, better or worse if there are ambiguous trees in the tree bank. This might lead to the oracle not always making optimal decisions, because alternative options will be available. And you can look into details about training the oracle, which you will need for the exercise. One example of training oracle, actually, what you will need for the exercise in the Jurafsky-Martin book in section 3, in section edition 3, in section 14.4.1. But there are also other approaches, so you might explore other oracle-based approaches. A baseline approach could select random, for instance, a random operation. This probably will not perform very well, but you can think about other ways of building an oracle. Okay. Are there questions to shift reduce? Because with shift reduce, we are pretty much done with syntax. What you've seen of syntax is different ways of representing sentences in terms of syntactic trees. In a phrase-based approach, you saw that the tree represents constituents or phrases. In the dependency approach, you saw that the tree represents directly relations between words. And we talked about two approaches to parsing these structures, the CQ algorithm for phrase structures, and shift reduce parsing for dependencies, and specifically for labeled dependencies, just mentioned here briefly. Are there any questions on this? Okay, if there are no questions, I would say we can swiftly move on to semantics, as if all of this is so easy and we're done with syntax. We by far not done with syntax, but in a lecture of just 1 2 hour slot per week, we can't cover a lot. I'm just going to wait a moment in case there are questions. And while I'm waiting, I'm going to remind you, in case there is still someone who would like to take the exam in an alternative mode as from the presence exam on the 29th, please send an email. I already got one email from one person who is not sure whether they'll be able to take the presence exam on the 29th, but if there are more of you, please send an email. Okay, if there are no questions, like I said, we swiftly move on to semantics. And semantics is the field of linguistics, or the sub-area of linguistics that studies the meaning. In general, the meaning of single words or clusters of words, phrases, and in the larger sense also of whole discourse, although the discourse semantics typically belongs to yet another sub-area of linguistics called pragmatics, which we'll talk about briefly, not next week, but the week after. Yes, the week after next. So how the question is basically, what do we mean by saying, what do words mean in general, and what do phrases mean? Here's an example of something that is not straightforward. The man's side, it's raining cats and dogs, he felt. This phrase, raining cats and dogs, when you think about it in its literal sense, and here is already a keyword, of course, would create a picture rather like the one here, whereas the picture that we usually see is not exactly the cats and dogs falling from the sky, but rather that of a heavy rain. This expression is known as idiomatic expression, and an idiomatic expression is one that whose meaning cannot be derived directly from the meaning of the individual sub-elements of that phrase. So you can't derive the meaning "it's raining heavily" from the phrase "it's raining cats and dogs," because cats and dogs have nothing to do with heavy rain. And the question is how to, in general, derive meaning of sentences. How do we know what sentences mean, and how to derive meanings of phrases from the elements of those phrases, and how to derive meanings of sentences from the elements of the sentences. The assumption is, of course, that the meaning of a whole is a sum of a meaning of its parts. This is a Freudian assumption. You have, of course, an example here that is a counterexample to this assumption. So, in general, what is meaning? You can consider meaning from various points of view. You can say, okay, meaning is the propositional content of a sentence in terms of validity or truth conditions. So here we view meaning in terms of inference. How can we tell if one sentence follows from another? Can it be automatically computed? These are questions that will that are main questions of a logical approach to semantics, logic-based approach to semantics. And here's an example of a well-known syllogism: all men are mortal. Socrates is a man, so Socrates is mortal. Represented in first order logic here. You could say the truth conditions of this you can derive truth conditions of the individual sentences and assert that this inference is valid. This is one approach, a rather high-level view on semantics in terms of truth conditions, where we ask whether a sentence is true. Very often, this reasoning requires, this inference requires common sense reasoning and also based on world knowledge. So some of the knowledge that is needed for deriving a truth, validity or truth conditions, the truth of a sentence, requires knowledge beyond the meanings of the words. So for instance, here, Max can open Tim's safe, he knows the combination, versus Max can open Tim's safe, he should change the combination. In one case, he refers to Max. In the other case, he refers to Tim, and we have to know that the pronoun can be resolved, to which entity the pronoun in each of the cases has to be resolved, and we use, for instance, world knowledge for this. So here, changing the combination refers to the safe, and so it's more likely that the person who has the safe should change the combination of the safe's lock. Whereas here we can use syntactic parallelism, for instance, to infer that this he is more likely to refer to Max because it's in the same syntactic position as the subject, as the referent in the preceding sentence, and also it's more likely that it's obvious that Tim probably knows the combination, but it's also an option that someone else knows the combination. So this is all world knowledge. Some sentences also may include content that is rather hard to represent in terms of validity of truth conditions, or even impossible to represent somehow validity or truth conditions, or in the logical sense for this content. Here's an example: emotional content. Poor, this qualifying adjective. It's rather hard to say which cat is poor and which is not. That or fortunately, what is fortunate, what is unfortunate, or what is not fortunate. It's also rather subjective. So expressing these modifiers here, these predicates, is rather difficult in terms of just basic truth logical, especially in classical logics, truth conditions. So how do we construct meaning? We will typically talk about a so-called linguistic form, so some representation of or some symbolic formal representation of a sentence's meaning. For example, here, all men are mortal, represented as a sentence of first order logic. We will also talk about context of use, so how to interpret meanings in context. This is an example. And we will also talk about lexical versus compositional meaning of sentences, where by lexical meaning we will mean the meanings of the individual words, and how to represent meanings of individual words, how to represent relations between meanings and senses of individual words, versus compositional meaning, that is a meaning of a whole as composed from individual parts. So for instance, how to turn this sentence, all men are mortal, into this statement of first order logic. This would be a task for compositional semantics. Why is it not? Oh yeah. Okay. Just show you. There are different types of meaning that can be identified within sentences that leads to issues not at so much at the directly at the semantics or literal semantics of the sentences, but which makes it clear that literal semantics or literal meaning of sentences is not enough. So to interpret the actual meaning of sentences, you need a lot more. Why is it so? Is it because in some cases it's more clear than in other cases what the meaning is in the given context, what the intended meaning is in a given context. In some contexts, it's uncontroversial. For instance, here, when you utter a sentence, it's raining, the meaning of raining is rather clear without any context. But it doesn't necessarily have to be the case, of course, that every word has this kind of unambiguous meaning. We'll get to ambiguity in semantics in a moment. There are also aspects of meaning that are beyond just the literal content of a sentence, linguistic content of a sentence, that also, however, somehow belongs to the meaning of the sentence, and from a computational point of view, it would be good to model it in some way. So, for instance, if you look at this sentence, these sentences here, it's perfectly dry outside. Are you mocking me? Well, what you see here is Max said it was raining. So he committed to something being the case. This it's raining is, aside from expressing the fact that some event is happening outside, is also expressing the fact that the speaker is committing to something. And here, this commitment is actually questioned. There are also observations related to speakers, especially in a dialogue context of a dialogue, private or speakers' cognitive states. So if we continue this dialogue, if you say, or do you want me to take an umbrella? So if we interpret this first sentence as a rather than a commitment to the event being the case, if we interpret it as a suggestion, then this sentence suddenly makes sense or becomes valid. This interpreted as a suggestion is recognized here by this clarification question. Do you want me to take an umbrella? So there must be a reason why Max said it was raining, even though maybe when looking out the window, the interlocutor didn't see the rain, but there may be a reason why he said that. There is an assumed reason that the interlocutor said that, because he's probably following some cooperative principles of conversation. So we interpret this initial statement as a suggestion. So not only as not necessarily as a commitment to something, but as a suggestion. And there's also a so-called social meaning, something that may even differ across cultures or across groups or across registers of speech. And this is illustrated here by these what looks on the surface as a question, but is not actually a question. Could you be serious, please? This is a request or request for clarification, or also request a suggestion of uncertainty. And this here is an explanation, but also an apology. And because something is something that is not preferred, and this linguistic behavior of mocking someone is typically a dispreferred behavior. This would explain why the apology is here, but also the elaboration, so explanation of the of why the apology is made. So aside from linguistic meaning in its literal sense, the linguistic form, there's a lot going on beyond what's just in the words. There are pragmatic phenomena that you see here. All of these are pragmatic phenomena, all of these illustrated here, that contribute to the meaning of a sentence, but that's not directly discernible just from the words of this statement here if it were used out of context. And all of these meanings, hopefully, we would like to model in computational linguistics. There's also other types of meanings that and other types of issues related to semantics that some of them are just let's say formal aspects of representing meanings, and others are rather important phenomena of language that need to go into a meaning representation. For instance, this sentence here, every student reads some book, is an example, a typical example of a so-called scope ambiguity, or an illustration of a scope of quantifiers. There are two quantifiers here, every and some, and you could ask a question. You could imagine that there are two readings of this sentence. There is another sentence of a similar structure that you may have heard of that also has two meanings. That sentence reads, every man loves a woman. And I will type it here and will ask you whether you see the two meanings. There are two meanings to this sentence that are related to quantifiers and the scope of quantifiers. The second quantifier in the sentence is the A. This is the indefinite article. If you've heard this sentence, of course, you know the solution. But those of you who haven't seen it might be surprised that there are two meanings. Yes, so each man loves a woman. What are the options? Exactly. So it may be that the theoretically possible meaning of that sentence is that all men love the same woman, because A is indefinite here, just like some book, but in principle it could be the same book. So the question is whether the qualifiers are in this order or in this order. So for all men, there exists a woman that they love, or there exists a woman which all men love. The same two readings are in principle possible here. Of course, most healthy humans will not immediately see that second reading where every man loves the same woman, because it's not plausible given the state of the world as we know it. Okay, we will not go into details about scope of quantifiers. This is in principle very interesting area, especially if you think about parsing. We just talked about ambiguous parses, and in principle, a good parser should be able to derive these two meanings with these two different scopes of the quantifier from a sentence such as this one. So that all the possible interpretations are represented. We already know that a single parse, oh my God, my word escapes me. single pass parser, this is what I was looking for, will not find the two readings. It will just find one of the readings. There are also word sense ambiguity. So a word may potentially have more than one meaning. We would want to represent these meanings. Making it is rather ambiguous, depending on what make means here. Of course, it depends on context. And there may be interesting relations that would need to be represented between, for instance, modifiers, especially in case of multiple modifiers of a sentence, and how to interpret multiply modified phrases. So an example here is the playbook. What does it mean that it's a playbook? That it's a book with which you play, or it's a book about plays, or what is it? So these are all specific areas of computational semantics that are active research areas in semantics. There are also phenomena in semantics that are outside of the literal meaning of a sentence, that cannot be derived just from the words of a sentence. I already mentioned the context dependence. These are temporal expressions, for instance, such as now and tomorrow. You have to know the context in which a sentence is uttered in order to interpret them. Same with locations. Here, there, that's a beautiful city. That is a is referring to something that appeared previously in the discourse. That's a beautiful city. Or referring to a speaker or the hearer. I or you have to disambiguate or somehow represent the interpretation of those pronouns. These are areas rather of semantics that rather belong to discourse, so the meaning beyond the literal meaning of the sentences. This was the scope of phenomena, roughly, briefly. This is by far not all of some of the more interesting areas of semantics. And we'll in this lecture we'll talk a little bit about lexical semantics. We will very briefly touch on compositional semantics. We'll mainly address compositional semantics from using statistical methods. We will not go into details of formal compositional semantics, which is, however, a very interesting area if you're into logics and formal methods in linguistics. Semantics is my area of interest, and semantics and discourse is my area of interest. So this is why I find all this interesting. Hopefully you do, at least some of you share this. Okay, but let's start with, in this case, bottom up, and first ask what is lexical semantics and what is the meaning of words. The lexical semantics is basically about meanings of words and meanings of structures that are larger structures that are composed of words, but that are not sentences, so-called multi-word expressions. And lexical semantics is about representing knowledge about word meaning. So without context, in isolation, just representing the meanings of words. This covers aspects of words such as word senses, semantic roles, and connotations. So how the different the words or multi-word expressions are to be associated in context, but without looking at that context, just looking at what the associations might be. Word senses are basically defined distinctions in meaning between different uses of the same form of the same word. And there may be shared meanings, of course, between different forms. So two different words may represent the same meaning. This is rather obvious. You can express the same thing with different words, and these words are referred to as synonyms. Semantic roles are those roles that are used in the that are that represent that are the semantic, let's say, that semantic equivalent of syntactic roles in a sentence. So in a semantic dependency tree, for instance, they will be the relationships between the heads and dependents, or in semantics we will say arguments and predicates, in the semantic sense. So I briefly mentioned it at some point that in dependency semantic representations, we saw some nodes that are purely structural. Those nodes include, for instance, determiners, those only structural elements that don't bear semantic content, or that bear certain specific, let's say, pragmatic content. The bears the meaning that the noun that it modifies is either unique or that has been specified by prior discourse. It exists already in the so-called common ground of that given discourse, in what is already known about that discourse. So semantic roles will be the roles in the semantic dependency trees. And connotation is the meaning that the word conveys beyond the truth conditions. So exactly that association that cannot be captured by true or false. Okay, how much time do we have left? 15 minutes. I think I will stop here and move on with word senses and with embeddings next week. With distributional representations next week. Okay, I think this is a good place to stop. Other questions? The slides are, by the way, always before the lecture on the on Moodle, so I hope you're keeping track of that. Okay, so if there are no questions, I would ask you to read through this. I will not manage to get you through this within these 15 minutes left, but I would ask you to read through slides labeled here 17 through to slide 25. And I will only very briefly start with different phenomena at the word level of word senses. This will make it faster. Okay, so 17 to 25. 17, 25, all about word senses. If you could read through, I will very briefly run through this in the beginning of the next slide, the next session, and move on to semantic roles. Okay. If there are no questions, I guess I will see you then next week.